All right, guys, today I wanted to talk about integrals and take a deeper dive into it. Previously, we had talked about the idea, the concept of an integral is to take the area under a curve or a function. And that's true, and I just want to be more specific. It's the area under, in quotes here, of the curve down to the x-axis. Okay, so it's this area that we're talking about here. And this can also be up to the x-axis if we have a function that's going into the negative region of the y aspect or the vertical function, the vertical variable that we're graphing. So we'll talk a little bit more about that. But let's just look at this example here so we can understand how this integral actually works. So we have y, which is some function of x, which is, looks like maybe x squared here. It doesn't really matter, but graphically this is what it is. Now, if I wanted to find the area under a function of a curve that is just a straight line, whether that's a horizontal line or a linear function that has a slope, I can break that up into basic geometry shapes, which we've done in the past, and last year we did in Physics 1 as well. But how do I go and break this up when I have a curve to a function? I can't just use straight geometry. Well, we actually will start with basic geometry. And so what I've done here is divided this area between our upper and lower bounds of some position x and initial position x naught. These are our bounds, upper and lower bounds of the area that we are trying to calculate with respect to this function. So you can have a inscribed or circumscribed aspect is what these two different methodologies are here. And these are basically approximations of the area. So I've divided up the area into little chunks of delta x so that you can see, and these are meant to be uniform changes in the x value, which will then create a column up to the function. Now in this case I'm taking the leading edge here, I'm taking the trailing edge, and you can see by the areas shaded that in this case I'm actually a little bit over the value of this area, and here I'm a little bit under the actual area. And again, the purpose of this is to make basic geometry shapes, little rectangles, to try to approximate the area under the curve. So if I were trying to find the area here, this little rectangle would be, the area would be, right, it's just the base times the height. So the base is delta x, and whatever the y value is, which I'm just going to call as the function of x. Okay, so I'm just multiplying these two, and that would give me the area of this column here. But what I need to do is somehow to sum all these up. But here's the thing. I don't want to just sum them up at this size scale here, because obviously the larger delta x is, the more error I'm going to have, whether that's greater or less than the actual value. And I really want to get to the actual area under the curve. And so what I need to do is drive this delta x smaller and smaller and smaller and smaller to the point where it's like infinitesimally small, which means as this gets smaller and smaller and smaller, the number of columns that I'm going to have is going to grow and grow and grow. So if my column width is infinitesimally small, that means the number of columns that I'm going to have is an infinite number of columns. And this is really what we're doing, is we're taking a limit sum, similar to what we did before, and mathematically this would actually give us the actual real value of the area with infinitesimally small widths and an infinite number of vertical columns. The smaller these get, the less the error I get for each one of these. So mathematically, the total area here, right, from our upper bound to our lower bound here, would be written in this fashion here. So we would say that the area total, I would want to take the limit as delta x approaches 0. I want to sum up all of the functions of x values and their corresponding delta x, which each one of those would be the same width, this infinitesimally small. Basically, all of the individual areas, I want to sum them up as delta x approaches 0. And what this is really equal to is the integral. This is how we would actually write this. So we use the integral function So it's like a long curly S. It's like an S that's stretched out. That's the integral function. And our upper bound would be x position. And our initial, this could be a and b. It doesn't really matter. I could take, if I wanted the area between here, it could be x1 and x2. It's between two different points in the x position here based on a y-x coordinate system here. So again, now I'm going to use this. Again, I'm taking this function, and instead of delta x, just like we did with the derivatives, we're going to use dx. So I'm going to integrate this function f of x across or along the x-axis here with respect to x between these two bounds. That is an integral function right here. So integrating f of x, this function, along x. So we're using dx. And so this is how you would actually write this. Okay? This is actually a definite integral, and this would give us the area entirely here, which I'm hatching out here in blue, which is what we're looking for. So this integral function gives us an actual real value rather than this approximation method using a limit aspect. Okay, so this is the definition of what it really means to have an integral of a function. And then of course, what that integral is giving us, that area under the curve, it depends what variables that we are graphing here in terms of what that area represents to us in physics. By the way, I want to just point out here before we shift gears is that if I had a function, okay, that let's just say looks something like this. And if I were going to go from, let's say, here is x1 and here is x2. So these are my bounds, my upper and lower bounds. Okay. The area in blue would be positive area, and the area in red here would be negative area. Okay, so you can have positive and negative area depending on where the bounds are, but in this case under the curve to the x-axis if you're below here. And the reason is if you were to look at, well, what are the y values of these columns, these infinitesimal columns, they're giving you negative y values. So it's going to give you a negative area. And so depending on what this is that we're graphing of these two variables, velocity versus time, this is going to be negative displacement and positive displacement. Work, if this is a force function over displacement, this is going to be negative work and positive work that's being done by this force because the force would be in the negative direction here. So understand that you can have negative and positive area as it relates to these integrals.